नमस्कार, सुस्वागतम, केम छो, वेलकम, राधे, दाबार्स, सत श्री अकाल, खंबागाड़ी, खुशामदीद, वेरी गुड आफ्टरनून। मैं अनिल भारद्वाज आप सभी का 86वें PRL के अमृत व्याख्यान में स्वागत करता हूं, अभिनंदन करता हूं। I, Anil Bharadwaj, very warmly welcome all of you for the 86th PRL का अमृत व्याख्यान। This is also the 11th PRL का अमृत व्याख्यान as a part of PRL का अमृत व्याख्यान 2.0 after we completed 75 episodes of series of Vyakhyaan, which we started on 4th of August 2021, celebrating the Platinum Jubilee of PRL, which is also a part of Azadi Ka Amrit Mahotsav as the country celebrates its 75 years of independence. PRL, as you all know, is an institute established in the year 1947 by the father of Indian space program, Dr. Vikram Sarabhai. And PRL Ka Amrit Vyakhyaan is a series of Vyakhyans to celebrate not only the 10th Jubilee of PRL, but also to cherish and relish the work which has been carried out by PRL in the area of physics and space sciences. Today, we have yet another very distinguished Vyakhyaan with us today, Professor V. Ramaswamy, who is the director of Geophysical Fluid Dynamics Laboratory at NOAA in USA, and he is also professor of Atmospheric and Ocean Science program at Princeton University. And he is going to deliver his Vyakhyaan on planet Earth in energy imbalance, the symptoms of climate change. The word climate change, you know all, is a buzzword, which is attracting a lot of attention, not only just from the scientists and bureaucrats, but also politicians and general public at large. So we should know what is the climate change and what are the symptoms of climate change, not attributing any phenomena to climate change, which is the general tendency of everyone to do so, that, oh, this is because of climate change. And to talk on this topic, who better than Sir Ramaswamy, who is going to talk to us symptoms of climate change. We thank Professor Ramaswamy to agree to our invitation of being 86th Vyakhyaan with us today in person in PRL. And to introduce him, I would now request Professor Ramachandran so that not only the colleagues over here in PRL in person, but those who have joined us live could know about Professor Ramaswamy. So, Professor Ramachandran, over to you to tell us about Professor Ramaswamy. Thank you.
Dear friends, good afternoon. I feel proud and privileged to introduce our distinguished guest and today's Vyakhyaan Karta, Dr. Venkatachalam Ramaswamy. Dr. V. Ramaswamy is the director of the NOAA Geophysical Fluid Dynamics, Princeton, New Jersey, Laboratory, Princeton, New Jersey, where he joined as a research scientist in the year 1987. Ram also holds the rank of professor in Atmospheric and Oceanic Sciences program at Princeton University. His primary research interests are radiative transfer, climate perturbations by greenhouse gases and aerosols, regional and global climate change. Ram, my sincere thanks for agreeing to spend some time in PRL despite your hectic schedule in India. Ram obtained his PhD from the State University of New York, Albany, and later he was a fellow of the Advanced Study Program at NCAR, Boulder, Colorado. At GFDL, he directs one of the premier climate science modeling centers of the world with the mission to construct advanced numerical models for understanding climate and climate change, and for making projections of climate in the future. His research has been published in more than 180 scientific papers. Ram has been associated with the IPCC since its inception and has been contributing to the same as lead author, coordinating lead author, and in various other roles. He is also actively involved in the World Meteorological Organization's scientific assessment of ozone depletion since its inception. He has played a leading role in the US Global Change Research Program reports and has served on the Joint Scientific Committee of the World Climate Research Program. Ram is a fellow of the American Geophysical Union, American Meteorological Society, American Association for the Advancement of Science, and American Physical Society. He is a recipient of many honors and awards and medals. To name a few, he is a US Distinguished Presidential Rank Award winner. He is a Department of Commerce Gold Medal Award winner and a three-time World Meteorological Organization Norbert Gerber International Award for Best Publications. Ram is a K.R. Ramanathan Professor in 2004 from PRL. I once again extend a warm welcome to Ram and invite him to give the Vyakhyaan today. Ram.
Dear friends, colleagues, greetings to you and greetings to those who are online. It's a real pleasure for me to once again stand behind this podium at PRL in the K.R. Ramanathan Auditorium, where I've had the occasion to talk, I think, a couple of times before, going back 2 decades. I enjoyed it then and I'm enjoying it now, coming here and meeting with a lot of old friends, colleagues, but also seeing newer faces here. Thanks, Professor Bhardwaj and Ramachandran for the kind introduction, very generous words. And I'm surely very, very happy to be here and to be welcomed like this. And thanks again for the hospitality. So I'm going to talk about something which, as Professor Bhardwaj already said, is a very contemporary subject of great interest to almost all sections and sectors of society, and that is climate change. And I want to talk about some specific aspects of climate change as we are coming to understand it, coming to grips with it. And that will be part of this Vyakhyaan at PRL today. So to just give you an outline of what I'm going to talk about, I'm just going to give a brief introduction to the lab I direct, the Geophysical Fluid Dynamics Laboratory in Princeton, New Jersey, and also say a few words about climate and Earth system modeling. I'm a new computational modeler, so you'll see my prejudice in coming from that aspect. I want to talk a little bit about heat imbalance and climate change, And I'm going to use the latest Intergovernmental Panel on Climate Change scientific assessment, which came out in 2021. I'm going to resort to observations of Earth's energy imbalance, what we are gathering from observations and how we are trying to interpret it. And I'm going to switch to a very pertinent topic under climate change, which is the energy-water nexus. Energy and water cycle are related, as you'll see when I come to my later slides. And in particular, I'm going to talk about two components which are products of human influence and how they are influencing the climate system, greenhouse gases and aerosols. And then how they introduce changes in the hydrologic cycle and precipitation. What do we understand about them in the 20th century and what is in store for the 21st century? And I told you I'm a climate modeler, computational modeler, but I'm also going to resort to observations because models and observations go together in trying to construct a scientific understanding. So first of all, a few words about the lab, the objectives that we have and the research strategy. So So the two objectives that we have, one is the development of comprehensive, integrated, and unified models of the Earth system, which comprises the atmosphere, oceans, land, biosphere, cryosphere, and ecosystems. So it's a big amalgamation of reservoirs, and that you have to kind of understand together in a sense together, and then not stop there, not just develop models, but apply these models for the understanding, prediction, and projections of the Earth system. And we call it seamlessly because we want to do it all the way from hours to centuries. If you want to understand the Earth system, you've got to really understand all the time scales. And that's kind of the motivation behind what we do in this lab. And this addresses the mission of the agency that we work in, National Oceanic and Atmospheric Administration. And NOAA comes from the Department of Commerce, so that's the Department of Commerce goals. And one of the things that NOAA mission has in terms of its why it exists is science, service, and stewardship. And you'll see that part of the science that we do has to have a scientific basis, of course, but it also has to serve society in some way. So the benefits are derivable for mankind as a whole. And on the right-hand side, you see kind of a sketch of what we call the pastures quadrant. So if you do a plot of along two axes, one for relevance for fundamental understanding and one for relevance for application, traditionally this quadrant is called the Bohr's quadrant, which is very high in terms of relevance for fundamental understanding. And this is called Edison's quadrant, which is for relevance for applications. Where the research in science lies is something which is akin to what Louis Pasteur did, which is that he did something which was basically very fundamental science. But of course, the pasteurization concept is a very important concept in everyone's life. So Pasteur's quadrant is kind of where NOAA research mostly lies. It does tail into Bohr's quadrant, Edison's quadrant, but this is kind of where the bulk of the science lies. So in effect, we have to do science which addresses the scientific peer community. Basically, you have to get the acquiescence from scientists, peer scientists about what you're doing as science, but it also has to be of value for societal impacts and service. So that's what we try to do. And climate increasingly is coming under that particular mandate. Okay, so I want to sort of just divert a little bit to IPCC and the fact that climate science has been now recognized, especially with the 2021 Nobel Prize to Dr. Suki Manabe, who's the sort of inventor of the mathematical modeling of climate, and for his work really on the impacts due to doubling of carbon dioxide, what it does for the climate system. And he did it back in 1967 with the first model of the climate system. That was in 2021. IPCC had a Nobel Prize in 2007, which was a Nobel Peace Prize, and that was awarded to IPCC along with to Al Gore, who was the Vice President of the US, for their efforts to build up and disseminate greater knowledge about man-made climate change. So climate science has been, over the last 15 years, been increasingly recognized as not just a valid climate science, but it's climate science that is actually being applicable and useful for society. So that's kind of given a lot of impetus to the fact that the physics of climate is an important subject to be dealt with, to be recognized. Now coming to what we do in terms of modeling the system, and this is kind of schematic, what you see on the left-hand side of a mathematical model of the climate system. So you have the atmosphere, you have the ocean, you have land, you have somewhere here's ice, I think. Yeah, somewhere here, yeah, ice sheet, you have ice sheet here. And then you have ecosystem. You have kind of creatures in the ocean, which are actually synchronized in terms of the life cycle, their life cycles, with the cycles in the atmosphere and ocean. The important thing to realize is that each one of these reservoirs, whether you take the atmosphere, the ocean, the land, they're all governed by equations. You can actually write mathematical equations to describe the cycle of elements in each of these reservoirs, but they all have different timescales and they all have different memories. So that's what makes this whole climate system quite complicated. If you had a system which has only oceans, you could deal with it because everything is water and you can write equations for water, which is uniform throughout the globe. Or if your system had only atmosphere, no oceans, nothing, you can write very simple equations for that and deal with just one system, one component of the Earth system. But instead, you have these components, which are atmosphere, oceans, cryosphere, biosphere, ecosystems. Each one has a different scale of motion. You can imagine all of them being fluids, really, because they're all fluids moving in a sense at different speeds. They have different memories, and all that makes for the complexity that we call the climate. And you have interactions going on between these systems, as depicted by these arrows, between the atmosphere, its chemistry, its ice, ocean ecology, biogeochemistry, ocean circulation. And then on the land side, you have land ecology, land use, land physics, and you have land ice sheets. So all these interactions make up your system. And then comes the computational aspects, which is kind of where I'm coming from. You can imagine the computational aspect consisting of really three axes. One is resolution, just the grid size that you take to represent the Earth system. You can make it small, you can make it large, but basically that resolution determines how much information you're getting from different parts of the globe. Then there's complexity. So you can make the system as complicated as you want to. That's dependent on the theory, the fundamental theory, the observations, and the equations you can form to represent the system for whether it's ideal tracers, carbon cycle, biogeochemistry, etc. And then simulation time. So for weather systems, you have to run the model just a few weeks, maybe. For climate, you have to run for a few decades to centuries. And then there's millennium. And then if you go on, there is ensembles of systems. And that's a little bit of a concept where you have to have different realizations of system in order to characterize the uncertainties. And all these three axes make for the computational aspects being needed to solve the equations for the entire system that you have with interactions between them. So that kind of is in a sort of nutshell, a brief description of what the system looks like. Of course, you can't do it on calculators. You cannot do it by simple algebra, and they're not analytical equations, which lend themselves to easy integrals and easy solutions. Instead, you have to resort to high performance computing to solve those equations. And the equations, as I said before, they are based on fundamental theory and some well-known laws of physics. So you have to have conservation, you have to have continuity, it has to have fidelity, and it has to have accuracy as much as is needed to characterize the system. And what the computers we do are located on a computer at Oak Ridge National Lab in Tennessee, which is where NOAA's high performance computing is located. And just to give you a sense of the scale of things that we're dealing with, so this computer came online in 2010, and at that time, we had kind of data of 17.6 petabytes, 80 million files. And now in 2022, it's gone up by almost more than a factor of 10 to 15 in terms of the especially data and files. And that's because as we are increasing resolution, complexity, number of ensembles, everything increases and jacks up the price of doing computations, which means that we are actually having to look at a lot of data. It really taxes the human drain a lot in doing that. All right, so some examples of where we are today in terms of computation simulations. On the top, you see actually the latest model that exists of the atmosphere, and this is around the world. So this is one of the in the frontier models. So this is 3.5 kilometer grid globally. So imagine every 3.5 kilometers you have a grid, and that is sort of over all parts of the globe. What that gives you, that resolution gives you, is the fact that you can really look at the circulation of the atmosphere in a great detail. And for example, you're seeing, for example, southern hemisphere, you have this very tight vortices and cyclones or anticyclones rolling around the southern hemisphere. You have natural vortices forming, which essentially become hurricanes eventually. So this model is the latest kind of model that is around the world. A lot of institutions have it now. What it allows you to do is to go all the way from clouds to storms to hurricanes and to weather and climate on very fine resolutions. And you capture a lot of interesting things in the atmosphere which you could not do in prior models, such as tornadic storms. Tornadoes occur on scales of about a couple of kilometers, and you need that resolution to be able to give these tornadic structures. And also the formation of hurricanes. One of the things that if you go to high resolution, what happens is you capture rotational motions very well in the atmosphere. And rotational motions are the ones that give rise to the extremes in weather, especially hurricanes and the cyclones. So to capture that this has been actually quite a remarkable advancement in terms of the science of how to do motions in the atmosphere. And then you can think of motions in the ocean. So this is actually ocean model with a resolution of 20 kilometers. And what you see kind of, this is a bit of a fast moving photographic image, but this is actually capturing the eddies in the ocean. The eddies are very important to be able to calculate the circulation in the ocean caused by movement of heat as well as salinity. And the eddies capture this on a 20-kilometer resolution, which is sort of the highest resolution reached by global ocean models. But in addition to that, now a lot of interest is there in the coastal systems. And 20 kilometers is not enough to resolve the coastal system. So for that, we need even finer resolution. And so we have this regional model, which spins off the same physics as this model. But this is a model showing the coastline of the east coast of North America. And what it's showing is the Gulf Stream. And you can see these sort of flows of warm and cold water in the Gulf Stream. And that's important because it's carrying heat from the tropical latitudes, the polar regions. And you see this being, and this is very important for not only the coastal physics, but also for fisheries and marine ecosystems, which is actually where this information is translating to in trying to merge it with fish population dynamics so that you can actually calculate the marine ecosystem behavior under changes in climate. Now, both these kind of models, they spin off the same physics, and perhaps you can't see this very clearly, but this is depicting all the physics that's actually calculated in terms of the global, regional, local processes. That includes things like conservation of angular momentum, conservation of heat, conservation of the water mass. And so you have interactions with the topography in the ocean. So you're taking care of all the known physics that you know exist in the ocean in order to actually get these circulations that you see in these models. And then just as a sort of another aspect of this study, of this progress, is the sea level prediction. So sea level prediction now is becoming an increasingly important exercise, especially on regional levels. And for that, you have to take into account all these different processes, not just atmosphere and oceans and ice sheets, but also groundwater, and also glaciers and the whole hydrologic cycle. And of course, sea level rise is expected to go up even more because of the melting of possible melting of the Antarctic ice sheet landmass. And that will add more to concerns of sea level rise. So all these processes are being taken into account using both the ocean model and things like ice sheets and shells and also groundwater. So let me get to now what I wanted to talk to you about, which is heat imbalance, which is occurring on the Earth's system and how it's leading to climate change. So first of all, we're all familiar with the fact that we have increases in greenhouse gases, carbon dioxide, methane, nitrous oxide N2O, and halocarbons, CFC11. And then, of course, some of this manifests in the ozone hole, Antarctic ozone hole. So ozone is also an important element, a gas in this respect. And everything is increasing, excepting CFCs, which because of the Montreal Protocol are now decreasing for the most part. And these are on the gases side. So these are the greenhouse gases. And then you have particulates, aerosols. Now, aerosols are a different kind of beast than greenhouse gases because there are several sources of aerosol. It's not just one source. And you have also sources which are natural in addition to being anthropogenic. So the frames here, which are entirely in red, are the human sources of aerosols. Ships, there's the smokestacks, automobile exhausts, diesel exhausts, aircraft. And then you have in blue, those which are natural aerosols. So this is coming from dimethyl sulfide in the ocean. This is coming from terpenes from vegetation. And then you have totally natural processes like volcanic aerosols from volcanic eruptions, sea spray, which emits sea salt aerosols. And then you have two components which can be both natural and anthropogenic. One is dust. Dust can be just natural, like from Saharan desert, Karakoram desert, or it can be dust due to the fact that land has been made arid because of man's influence, and that also can cause emission of dust. And then there's forest fires, which can, of course, be caused by just natural burning because of lightning, for example, triggering a fire, or it can be unwanted human influence, which kind of creates fires in the forests. So you have aerosols coming from a variety of different sources, which adds to a lot of complexity, unlike the case of the greenhouse gases. And in terms of aerosols, the processes so for greenhouse gases, the thing that they do to perturb the climate system is they trap infrared radiation in the system. So that helps the system to accumulate more energy. In the case of aerosols, the processes are a little bit more complicated. When you have aerosols, you can actually have either reflection by them or you can have absorption because they can have the absorbing aerosols. And as the aerosols are emitted from the surface, most of the human aerosols are emitted from the surface, you have advection of the aerosols from one place to another. Aerosols can also be inside clouds, and through a process called aerosol-cloud interactions, they can make the clouds brighter, which causes more reflection. There can be also absorption. But again, these two processes culminate in how aerosols perturb the climate system. And what IPCC has done, this is the Intergovernmental Panel on Climate Change, they have assessed what the effective forcing is from these components from pre-industrial to present times. Pre-industrial 1750, present times is about 2020. And what this diagram depicts, and I think we will not get into a lot of complexity in this, but the thing to note from this is there are positive values, which are in red, and there are negative values, which are in blue. So the biggest positives are from the greenhouse gases. CO2 dominates. Methane and nitrous oxide N2O comes closer to about half of CO2. And then there's ozone from the troposphere because of pollution. And that builds up some of the positive energy into the system. So all these three things actually cause a warming of the system. They tend to cause a warming. And then you have in blue the aerosol effect, which actually causes a cooling of the system, largely due to that effective net reflection of sunlight. The one thing you notice is that the uncertainty bars for greenhouse gases is smaller than their mean value. You look at 2.16 for CO2, and the range is 1.9 to 2.4. So it's effectively well capped. But the aerosol one has a very large uncertainty bar, and that's because the two things which happen in the aerosol which are complicated. One is their sources are inhomogeneous. They are kind of located, distributed throughout the globe. But in addition to that, what happens is that they have very short lifetimes. So unlike CO2, which when the moment it's emitted, a moment a molecule of CO2 is emitted, it is really there throughout the entire globe for centuries maybe. But aerosols are short-lived. lifetime is only 5 to 7 days. So an aerosol particle emitted has a chance of coming out of the atmosphere in 5 to 7 days. And that difference in time scale represents a complexity in the whole process of how to deal with it. And so that creates this uncertainty bar that you see for aerosols, which doesn't exist for CO2. And so when you look at the total anthropogenic forcing that's arisen in the system, it's largely dominated by greenhouse gases, minus a little bit compensated by the aerosols. But the uncertainty bar is large because of the fact that the aerosol uncertainty bar is large. So the net total anthropogenic forcing comes out to be having a larger uncertainty bar than any of the greenhouse gases do because it's dominated by the aerosol forcing. And that kind of really creates uncertainty in the sensitivity of the climate, in our estimate of the sensitivity of the climate system to anthropogenic forcings. So what are the symptoms of an unbalance? So that's the imbalance from the pre-industrial times to present. What are the typical symptoms of an unbalanced Earth? Well, everything, temperature, the moisture, mean sea level, ocean heat content, and then, of course, the impacts on society in terms of coastal flooding, erosion, droughts, floods, glaciers melting, and extreme events, evaporation minus precipitation, creating extremes which are arising due to the fact there's an imbalance. So that's sort of a schematic of it. If you look at the totality of really what's all is happening, this is all from observations. You have multiple lines of evidence. You have multiple lines of evidence for a warming world, which includes not just the temperature, surface temperature, air temperature over land, sea surface temperature, all of them increasing. And then you have humidity increasing because there is more evaporation, the humidity increasing, snow is decreasing, glaciers are retreating, Arctic sea ice is decreasing, and ocean heat content is increasing. So all these are, it's not just temperature only that is increasing and causes a warming, but all the accompanying things that come alongside the warming of the surface. So there's no question that there is this imbalance has led to a warming, well established now in the IPCC assessment documents. And the IPCC describes how, for example, you take the account of the forcing, and then, of course, there are feedbacks in the climate system, which then highlight the forcing even more. They amplify the forcing, and then they give you the climate sensitivity. And in terms of where the heat is going in the system, 91% is going into the ocean. A, because the ocean is 70% of the Earth, and B, the water has a large heat capacity. And so a lot of the heat is going into the oceans. Land is taking up about 5%, mostly in terms of soil moisture. Ice is about 3%. Atmosphere retains the heat only to 1%. So most of the heat is really going into the oceans, and that's kind of what then causes all the things happening in the ocean circulation. And by virtue of the ocean warming up, the ocean air interactions create more of an imbalanced system. And to just sort of go into a model schematic of how you sort of solve this problem. So in a model, you have the ocean, the sea ice, you have atmospheric dynamics and physics, including all sorts of physics processes. Then you have chemistry, which kind of takes into account both the gas phase and the aerosol phase, a land model, and then you have as inputs the emissions to the best of our knowledge, the short-lived pollutant emissions, which is mostly aerosols, and then gases such as methane, N2O, and then the CFCs and CO2, etc. So this is all going into what we call a climate model. You saw the schematic earlier. This is a little bit more details of the processes that go in. And I'm not going to go into the details of these processes because that would be a sort of a seminar by itself. But instead, I'm just going to focus on what kind of results you get out of models like these, which are, by the way, models that are now in use almost in several centers around the world. So IPCC looks at all these models to see what they produce. And what they produce is this, that if you take all the models, and those are shown with the envelopes here, and you take into account all the natural and human forcing, that's the curve you get when you plot it as a function of time for the surface temperature. the observations are coming in black, and the model mean of all the models in the world, so it's not just the GFDL model, it's all the models from the world, use the orange line, you can see that the models are capturing the observations pretty well. Now, if you consider only the natural forcing, and this was a sort of powerful argument that IPCC makes in trying to argue that human influence is discernible in the climate warming. If you take only the account of the natural forcing, which is just volcanoes and solar forcing, you get this. So you get no change at all when you take into account just the natural forcing. So you need the anthropogenic forcings to get this difference and therefore to come close to the observations from about 1970 onwards. You can see from 1970 onwards, the rate of increase has gone up. And that's kind of what really clinches the argument about all the warming and the, not just warming of the temperature, but also the warming of the entire system, climate system, is due to human influence. You can't get it any other way. Okay, so now let me focus in on the imbalance as observed. So it's a pity that we really don't have observations, continuous observations of the Earth's energy at the balance at the top of the atmosphere from pre-industrial to present. Of course, pre-industrial, we didn't even know what was happening. But even since the time when it was recognized that CO2 would warm the climate system, we really didn't have any satellite measurements which could give us the entire picture of the Earth's energy from, let's say, 1960s, 70s onwards. The satellite measurements era started in the late 60s, maybe 1979 would be the date when continuous measurements started. But unfortunately, the energy measurements did not start in a continuous way till 2002. So we have only about 18, 19 years of measurements of the Earth's energy balance at the top of the atmosphere, which means that you're measuring the solar energy coming in, the solar energy going out, and the infrared radiation which the Earth has to emit to balance whatever is coming from the sun. So we have this only for 20 years, but we have putting together observations and models together. We have been able to learn a lot about what's been happening over the last 20 years. So it's instructive to see where it lands us in terms of what we understand has been happening in the climate system since pre-industrial times. So in looking at the schematic of the energy balance of the Earth, and this is sort of top of the atmosphere, so you're looking down at Earth from space, you have 340 watts per square meter. The watts per square meter is a flux unit. So it's the energy per unit time per unit area. So 340 watts per square meter is coming in, 100 is going out, so net coming in is 240. And for the Earth to be in balance, the same amount of energy should be going out. Otherwise, the Earth will be continuously warming or heat cooling. But you see, there is an imbalance here of 1 watt per square meter. This is, within uncertainty limits, but it's within the uncertainty limits, it's 1 watt per square meter. And I'll come to the surface issues later, but this is the top of the atmosphere picture. That's what we are seeing now. And in terms of the time series, this is the time series that you're seeing from the satellite of the Earth Energy Imbalance, EEI. So the change in EEI is plotted here as a function of time. And you see that, there's a lot of variability, but there is, if you draw a sort of line through it, it is actually increasing at 0.4 plus minus 0.2 watts per square meter per decade. So which means in 2 decades, you've gone up by about 0.8 watts per square meter in imbalance. And that is the part. This is now a documented increase of observations. So how to explain it? And I'll sort of make a long story short here. We've tried to explain it. So how can it change? So either you have internal variability. So the system may be varying internally, giving you that increase. That's a plausible solution. Another possible solution is that the relative forcing that we know acted on the system over this time is causing this increase, or it's the feedback. Feedback meaning changes in the water cycle, changes in clouds. That's a feedback. So we parsed out these, we've analyzed these 3 quantities. One thing you can rule out is internal variability. That there just isn't enough, there just isn't evidence to support that it can be due to solely internal variability. That's probably some component due to internal variability, but not the major part. And what we, okay, so just before going into the sort of reasons for it, uh, the climate system is out of energy balance now, and most of this energy is going to the oceans, as I mentioned earlier. So in terms of what is happening, so there's been changes in both the short-wave radiation part of the part of the balance and the infrared radiation part of the balance. I won't go to the infrared part because that's actually very small. Most of the changes are occurring in the fact that over these 20 years, there's been a large decrease in reflected sunlight. And this has come due to three reasons. Two reasons. One, in the issue of forcing, there's been a decrease in aerosols. So what happened was in the 1970s to 2000s, globally, there was an increase in aerosols, particulates. And then after the period of late 1990s, several nations stopped or decreased the emission of aerosols. North America and Europe were two of them. And then later on in the early part of 2000s, it was China. And so the aerosol decrease has contributed to a decrease in reflection. Also, there's a rapid cloud adjustment due to greenhouse gas increase, which actually increases cloudiness and therefore increases reflection. Decreases cloudiness, therefore decreases reflection. And then the sea ice decreases, primarily in the Arctic, which has also reduced reflection. So this is what produces or explains the most of the change that's happened in the terms of the decrease in the reflected sunlight. And okay, so that's coming about because of these three reasons, and that's a big change because the aerosol changes actually and the sea ice decreases have been big factors in terms of the reduction of reflected sunlight. So let me just now digress to one other aspect coming out of this energy imbalance, that is the energy water cycle nexus. And I'm going to kind of switch to the longer time period here to talk about the hydrologic cycle. So going back again to the energy diagram or the diagram of the energy estimate. So I talked about the top of the atmosphere earlier. Let me talk about the bottom of the atmosphere. So there's 160 watts per square meter estimated of absorbed solar at the surface. And again, in the infrared, you have to have some compensation. So the surface emits 398 watts per square meter. This is a Planck effect, Planck emission going as sigma T to the 4. And so it's a T to the 4 effect. But there's also a downward radiation because there's increase in greenhouse gas in the atmosphere, water vapor CO2, so that increases emission downward. So you have 342 coming downward, so this net is about 56. So net long wave loss at the surface is 56 watts per square meter. The net short wave absorbed at the surface is 160 watts per square meter. The difference between these two has to be taken up by evaporation from the surface and sensible heat and latent heat transfer from the surface, which amounts to 103 watts per square meter. And most of the latent heat is due to evaporation. So on a global scale, this is how the surface balances the heat, but it involves water too, because evaporation involves water. And just as a sort of an additional fact, and one of the observations is that latent heat dominates. It's 4 times the sensible heat in terms of a global average. So this is how the energy water thing comes into the picture, because water at the surface is the important component completing this cycle. And okay, so this is just amplification of the hydrologic cycle. And there's a lot of things happening with water, including things like storage, groundwater. I'm going to focus on just evaporation and precipitation, just the fact how much evaporates and then how much then precipitates because of the fact that evaporation is going on from the surface. All right, so this is now honing in on these two significant forcing agents, greenhouse gases and aerosols, and talking about the impacts on the global hydrologic cycle. So now I'm going to go to simulations done out of the models at GFDL. And if you look at surface temperature change, so this is sort of, you saw earlier the IPCC map of taking all the models together and looking at the simulated change due to natural agents and natural plus anthropogenic. But let me talk about just the one model here, this is the GFDL model, and talk about the offset of the greenhouse gas effects by aerosols on temperature. So, with a computer model, you have the liberty to ask the question of what if you did this, what if you did that, what if you did something else? The real Earth doesn't offer you a comparable laboratory to conduct an experiment like that. I mean, you wish you had another planet where you could tweak CO2 and then see what it does to climate change, but you don't have that. Computer is your model, basically your lab. Computer is your lab, and the computational model is a model that you have to use to ask these questions. So if you ask the question of what happens if you just increase greenhouse gases from pre-industrial 1860 to 2000, you'd get this pink curve. Observations are in black. So you see the pink curve overestimates the black. It kind of has the right ascendancy, but it doesn't have the right magnitude. The aerosol, if you're driven only by a tropospheric aerosol, then this is the green curve is what you would get. And then if you have the other four things, which is kind of everything else, you'd get the yellow curve. And then this blue curve is the residual from all of them. And that comes close to the observed, not exactly, there's still sort of a bias, but it kind of matches the flow in the observations. And that's really being compensated, that's really a net effect of the greenhouse gas change, the aerosol change, and all the other components changing, including land use. So the important part here is how much the offset has been. The greenhouse gas change only, where I mean 1.5 Kelvin, aerosol cools to minus 0.5. So residual is about 1 Kelvin, which is of the order of what the temperature rise has been over the last 175 years. I'm going to change to precipitation now. So in precipitation, it's a different picture by how the compensation works by the aerosols. So here again, you see the pink curve, that's only greenhouse gas. If it was greenhouse gas, you would continuously see this large change in precipitation. And this is in units of watts per square meter, but no, don't worry about that. Just look at the units here. Whereas the aerosol only is minus 1.8 watts per square meter. So it's almost a complete offset of the precipitation, unlike the temperature change where the offset was only by a factor of 1/3. And the observed change is this in black, and the model is in blue. So it's precipitation is a very difficult variable to simulate. And so you expect more biases in precipitation than for temperature. But nevertheless, this shows the compensation that the aerosols have exerted with respect to greenhouse gases. Remember, they have opposite effects in terms of their relative tendencies, but the aerosols are seemingly having more effect in terms of the offset of precipitation. Most of the precipitation change, I'll sort of rush through this, it's sort of a little bit of a secondary point, is coming about because of changes in Asia. This blue bar represents the change over Asia. Most of the changes happening over Asia. Somewhat this is related to the fact that most of the aerosol effect is also over Asia. So to analyze kind of how, oops. All right. One thing you might ask is, so what do the observations say? This is what the observations say. If you look at the Northern Hemisphere summer precipitation anomalies, the observed gives you this decrease over this period between 1970 and almost 2000. And then it kind of hits back to normal levels. But this decrease is really very striking because leaving aside all the model results, if you had, there only can be two reasons why it can be decreasing. One is internal variability. So you have to postulate that there's some internally variable factor which caused an oscillation like this of maybe a 30, 40-year period. That seems unlikely. Most of the plausible reason is coming about because it's been due to the radiative forcing that has been exerted on the system. And if you look at the corresponding change in the observed summertime short-wave radiation, you see again the decrease over this period. And that decrease has been caused by aerosols. So it stands to reason that just in a correlative fashion, in a correlative sense, you have this striking correlation between the reduction in the short wave and the fact that there's been a concomitant reduction in precipitation over this period. If you look at all the models, they are, if you look at greenhouse gas only, you see that's increasing. Just like we saw in the previous curve, greenhouse gas will always tend to increase the global hydrologic cycle, the intensity of the cycle, it'll be increasing. Aerosols alone, which is AER, is going to be decreasing, And the net of all the models is this red curve, not exactly a resemblance to the observed decrease, but nevertheless, it is suggesting a decrease as opposed to just looking at greenhouse gas only. So again, ignoring the fact that there could be an internal oscillation, then forcings really caused this decrease. And from the GFDL model, we can analyze kind of why it comes about due to these different components. So look at first the fact when the model is run by well-mixed greenhouse gas only. So here, what's happening is the long wave radiation is causing an increase in the surface, in the gain by the surface. That's because there is more increase in the long wave that's coming to the surface. And the surface has to balance it by releasing more latent heat, which is the loss of heat from the surface. And that is loss of heat from the surface means there's more evaporation. So there's more water going into the atmosphere from the surface because of the fact there's more long radiation coming into the surface. For the aerosol, the change is the decrease in the short wave. Radiation is decreased at the surface, so there's less evaporation, which means the surface actually gains latent heat. It doesn't release enough water. So there's actually a desiccation and therefore a decrease in the precipitation. So, and then if you look at all forcing, which is combined, everything combined, you see this large compensation between the long wave changes brought about with greenhouse gases at the surface and the short wave reduction caused by aerosols. Now, going back to the diagram earlier of the forcings, I said the aerosols have a large uncertainty. So there's definitely large uncertainty about this part. But nevertheless, it does suggest that there's been quite a good deal of compensation of the greenhouse gas effect. If there were no aerosols, for example, you'd be left with just a blue curve, and which means that precipitation would have had to increase, but it did not. Aerosols did another thing. And I'm looking at the time, and how much time do I have? 5 minutes. Okay, so it's just 5 minutes. I'm going to shift quickly to some other points here. So aerosols have also induced shifts in the rain belts. And this has been noticed, actually was noticed in the IPCC 2007 report, where if you just look at the observation, that's the black curve here, you see that just north of the equator, there's been a decrease in precipitation, whereas south of the equator, there's been an increase. And this is actually well explained, and I kind of have to adjust the explanation here. This actually was also noticed in an earlier study where it was noticed that the Indian monsoon weekend, there was a north-south shift in nation rainfall, and there was a Sahelian drought, which is indicated with the reddish portions here, all because of the fact that all the aerosol effects occur in the northern hemisphere, because all the pollution aerosols are in the northern hemisphere and really not much southern hemisphere. So there's much more of a solar radiation deficit in the northern hemisphere, which causes a shift in the rain belt, or what's called pushing southward of the ITCZ, intertropical convergence zone. And that's kind of manifest in this. And just to sort of explain physically, what's happening here is that the Hadley cell is being weakened because of the fact that aerosols are reducing the solar radiation in the northern hemisphere. Therefore, there's less heating in the northern hemisphere. And so the combined effect of greenhouse gas and aerosol is that the aerosol weakens the Hadley cell, the greenhouse gas weakens the Walker cell, and that's a net effect you see in the simulations, which take into account both the greenhouse gas and aerosol changes. All right, so 21st century, the scenario calls in general that the greenhouse gases will keep increasing. I mean, we're not talking about mitigation measures yet, but generally, if there are very little mitigation effects, greenhouse gases are going to increase, CO2, methane. But the aerosols are going to decrease because nations are getting rid of aerosols because they are a visibility factor, and they also affect health and mortality. And generally, it's very noticeable that the air is not clean. And so there's a push for nations to reduce the aerosols. So if that's the case, then our theory or understanding of the way the climate system works should mean that everything should be reversed, that we should have a reversal of the late 20th century effects. And indeed, in models, that does happen, because if you see now in these simulations, we are here in the present, and this is from 1850 to 2020, which is kind of, you saw earlier up to this point. And then beyond this point is the projections. And so if you look at, again, just the all forcing for sake of brevity here, you see that is coming along like here. And the black line, by the way, is the observed precipitation. So there's a decrease in the all forcing caused by the aerosols, and then there's an increase because now you have the aerosols going off, and therefore there's a release of the effect that the aerosols had on choking the precipitation. So now the system is going to take off after the greenhouse gases, which are increasing, the aerosols are decreasing. So these two add up now to an increase in the precipitation. It's actually northern hemisphere precipitation. So the picture that one can construct out of this is something like this, that coming down from 1900 to about 2000, you had some effects of greenhouse gases in the early part of the 20th century on precipitation. And then there happened this decrease because aerosols were increasing. And then as aerosol effects go off, then the system becomes dominated by greenhouse gases. So there's actually now a good deal of speculation that what we've been seeing in the last 10, 20 years, the warming that's being seen, and including therefore the extremes, maybe due to a large consequence, or maybe a large consequence due to the aerosol changing, aerosols decreasing in the atmosphere, or what is being called as the unmasking of the aerosol effect. It is not entirely due to greenhouse gas yet. That might come later because the greenhouse gas are accumulating in the atmosphere. The effects of that may be delayed to maybe the next decade and so on. But right now, it may be this unmasking effect that we are seeing, this rather very dramatic effect that we are seeing on extremes in precipitation, for example. And again, going back to the physics of the surface heat balance, now you see relative to 2000, the net short wave is increasing. Net short wave into the surface is increasing because aerosols are decreased. The net long wave is increasing because there's more greenhouse gases. And so the latent heat lost on the surface has to increase, which means more precipitation than before, which kind of goes alongside the previous plot. I want to quickly talk about changes over India in the context of what we just talked about. So again, you can sort of go through the argument of running the model with just greenhouse gases. Actually, it's the same run, it's just showing India now with greenhouse gases with aerosols only. So if you look at all forcing changes in, if you look at all the changes in the temperature, you see some of the warming occurring over India. This is the wrong picture here. Okay, so this is the surface temperature picture, and most of this change is coming about because of greenhouse gas changes, as well as some aerosol changes, which is actually due to black carbon. And then if you look at precipitation changes till now, this is the change in temperature from from 2000 minus 1950, so the last half of the 20th century. This is a change when you go forward from 2000 to 2050. So, it's obviously getting more warm. The scale is the same. So you're getting more warm here because now you're getting more and more effect from the greenhouse gases. And you see a slight cooling due to aerosols because the black carbon effect is going away because of reduction in aerosols. And the other aerosols, the scattering aerosols, are taking over. More importantly is the precipitation, where you see the weakening of the Indian monsoon over the latter part of the 20th century, giving you this decrease in precipitation, which is being offset which is an offset between the increase in precipitation to greenhouse gases and a decrease caused by aerosols. And as you go forward into the future, you see sort of increase in precipitation all over India because of the fact that now aerosols are giving you an increase and greenhouse gases are giving you a further increase. So this is the kind of the natural follow-up of the physics from whatever we expect in the late 20th century. So obviously where we are going with this is actually using these kind of models in terms of prediction so that we can actually try to predict these extreme events due to the fact, at least one of the facts, that the hydrologic cycle is getting more and more vigorous and intense. And so finally, this is the conclusion. The aerosol effects of hydrologic cycle is kind of the principal message I want you to take from here, which is the anthropogenic aerosols have offset the precipitating impact of greenhouse gases. Most of this has been in effect in the Asian region. And so this begs the question of, did aerosols actually suppress what otherwise would have been a greenhouse gas induced precipitation signal in the latter half of the 20th century? Have we actually delayed the greenhouse gas signal because of the fact that aerosols entered into the picture? Subtle observations reveal signatures of the changing atmospheric composition, and this includes changes in greenhouse gas and aerosols, but for the last 20 years, it's been a large in effect due to the aerosols. The recovery from aerosol effects in the 21st century is going to just shift the whole thing into the other direction and cause an increase in the vigor of the hydrologic cycle, which means an extremes in most places. And one of the things that I didn't have time to dwell on is the impact of the increasing water vapor in the atmosphere. So water vapor, amplifies the surface warming, obviously, because more moisture means water vapor is a greenhouse gas, so there's more increase of the long wave effect. But water vapor does another thing, which is it actually also causes release of latent heat in the atmosphere, and that increase of latent heat causes significant increase of rotation motion. Rotational motion gives rise to storms, and storms means more extremes. So in a sense, the water vapor increasing into the atmosphere as a result of all the CO2 and methane increase is actually contributing to an increase even in the rotational motions, therefore the extremes like storms. So I think that's all I had. Thank you very much for your attention. Sorry, I took a little bit more time. I'm open to questions, if there are any.
Thank you, Professor Ramaswamy. It was a very informative and comprehensive take on climate change. And especially there were many new aspects that you brought into discussion through extensive climate model simulations. And kind of you segregated the effects of greenhouse gas aerosols, and also not only temperature, you also discussed a lot on hydrological cycle. That was really interesting. So I am hoping that there are some questions from the audience. So let's take some questions. Yes, Professor Tay.
Thank you, sir. I have a question regarding this aerosol. I mean, do we have observation that aerosol have actually decreased so that greenhouse effect is taking over? I mean, or it's just a prediction?
Sorry, are you asking whether aerosols have decreased?
Yeah, I mean, you are suggesting that so far aerosol, because of the aerosol loading, greenhouse effect was not pronounced enough in last 20, 30 years, but now in future it will take over because you will have less loading. And do we have observation for that? Or is just a model prediction?
No, there are observations. I mean, the MODIS data, for example, clearly indicates the aerosols have decreased over the northern hemisphere, especially mid-latitudes. There's a clear decrease in optical depth in the MODIS and MISER data. But we're talking about northern hemisphere. That's kind of where the aerosols were, especially over the Chinese region. The aerosols have decreased significantly. Also, the aerosol effect has decreased over the oceans. And you can see that again in the reflected sunlight data. I kind of went over this briefly when I was looking at the decrease in reflected sunlight. Okay, so you see in this plot, these are contributions from various regions. This, I didn't go over this part of the plot, but here is the observed reflected shortwave trend, which is minus 0.6 watts per square meter per decade. This is actually the best model representation, accounting for all the forcings and feedbacks. It doesn't even come close. It comes to only half of that. But where this comes from is mostly the tropics and the northern extratropics. And you can see that, satellite data, this is the tropics, this is the extratropics. So that's kind of where the decrease is coming from in terms of the global mean. So it's a clear indication of this is a zonal mean, but in the zonal means, there's a clear indication of decrease in the total aerosol optical depth.
And how did that happen? I mean,
How did that happen?
yeah, I mean,
I have only partial answer for that because there's been reduction in emissions. both in North America and Europe and in China. There's a clear reduction of emissions. It's clearly noticeable even in Aeronet data. So it's kind of there in different data sets. But this one is from satellite observations.
Sir,
So, I mean, this decrease you see here in the global is very large. Got to find out how it happened. But aerosols clearly are a factor in this. Because what else can there be in the tropics and in the northern extratropics? What else can there be?
Yeah. In one of the slides, you showed a very interesting model output where there is a step kind of decrease between 1975 to 2000, where is the
In precipitation?
Yeah.
Yeah.
In precipitation, in competition between greenhouse gases and it's taking over. One is taking over the other. And I was very surprised to see the drastic jump between these two. Yeah. The jump between the sharp decrease before 75. So it's quite interesting. And then the gradual, after that decrease, maybe 25 years, and then it starts taking over gradually, and the greenhouse gases starts becoming dominant.
So the different things between, so if you look, so I didn't again go over the individual curves, but this green curve, look at just the greenish curves, CM4 Southern Hemisphere and CM4 Northern Hemisphere. So Southern Hemisphere, there's not that much that happened, which is logical because there's nothing happening except in greenhouse gas. Northern Hemisphere, on the other hand, sees a big dip because this is the time when, at least according to the emission data, this is when the aerosols really hit the max. Part of it is the fact that in the post-World War II, the industrial activity really spurred a big increase in emissions, at least in the emissions data. So this is reflecting just a consequence of whatever the emissions data was that the models had. You're right. I mean, it is a sharp drop, but that's kind of where it's coming from.
Other questions? Meghna.
Thank you, sir, for a nice talk. I have one follow-up question. As you have showed that aerosols has been decreasing, and you mentioned some particular areas where they are decreasing, but we know that there are many common sources for aerosols and greenhouse gases. So there is remarkable decrease in aerosols. So at least some reductions in greenhouse gases should be seen, at least in those particular areas. So does observation show some in-hand decrease between greenhouse gases and aerosols?
You mean the greenhouse gases also decreasing because of
Because they're
decrease?
common sources, yeah.
Yes, sure. From the common sources, you would expect that, like smokestacks, reduction would be there. But greenhouse gas, I mean, the CO, okay, so I don't deal with CO2 and methane separately. If you take CO2, the major source is not the same as for aerosols. So wherever the source is common, yes, it would decrease. But I believe the major source for CO2 is different because it is actually it's power plants, but it also cement production, and it is also, others may be able to say it better, but there are some differences between the aerosol sources and CO2 sources. Methane is entirely different. Methane has other sources. So I don't think you can draw too much from how much the aerosol decrease should have also resulted in CO2 decrease, because the sources are quite, there'll be some reduction in the same source, but most of the CO2 is not coming from really all the sources that aerosols are coming from. So that would be my speculation on that.
Okay, and I have another question. You have shown one graph of precipitation and shown some sensitivity simulations, including greenhouse gases and aerosols. And on the top of it, you have shown radiation graph. So radiation and decrease in precipitation, one like hand in hand. But so as we see that neither aerosols nor greenhouse gases were able to capture the reduction in precipitation pattern. but the radiation was coherent with this.
Is this over India?
No, you have seen a global. Yes.
This one?
Next one. Yes. So yeah. So SW radiation anomalies were decreasing during that time where precipitation were decreasing. But neither greenhouse gases nor aerosols were able to capture that much reduction. So what could be the possible factors?
Yeah, lots of factors. One is that the radiation anomaly to the surface is really the all sky. So it is not just clear sky, but also includes clouds. So it's possible the models are not capturing the changes in clouds. And that then could also be reflecting in the fact that convection is not being captured well, which means the precipitation wouldn't be captured well. So there are lots of reasons for biases in precip data. For the radiation data, I believe it's the clouds which are making a big difference.
Thank you.
Professor Bharadwaj.
Excellent talk, Mr. Ramaswamy. I just wanted to have two clarification. One is when you talk about increase in the greenhouse gases, do you include water vapor in it or no?
So water vapor is mostly regarded as a feedback variable. So when I'm talking about well-mixed greenhouse gas increase, it's just CO2, methane, N2O, tropospheric ozone. Those are the increases. Well, that's actually not well-mixed. So it's only CO2, methane, N2O, and with a slight reduction in CFCs. Water vapor is a feedback variable. So that is not regarded as part of a forcing agent. It's more a feedback agent. But of course, when you do the analysis of the budget, energy budget, water vapor comes into the picture because of that connection to energy. So greenhouse gases, in a sense, are forcing an energy imbalance. Greenhouse gases and aerosols are forcing an energy imbalance. Water vapor is reacting in the water part of that connection. But water, it's a cycle. I mean, it's a vicious intersection because water, by being in the atmosphere, start behaving like a greenhouse gas. So it's then having an effect on the energy. So when we analyze the surface energy budget, it is more forcing and feedback that you're looking at. It's not just the forcing aspect. So yeah, so that's a distinction I'd make.
I see. Okay, thank you. And the second question is that if you predict that aerosols is decreasing and greenhouse gases are increasing, what will be the impact on the cloud cover?
On what?
Cloud cover.
Yeah, that's an interesting question. That's going to be uncertain because we don't know. We don't yet model the clouds very well, even for present day climate. So the uncertainty factor for how clouds will change in the future is also uncertain. It's not that we don't know anything, but it's just that it's uncertain. So as to what will happen to the clouds, it is difficult to say because clouds at different levels alter the feedback differently. If you had a scenario where only low clouds were changing, if low clouds were, let's say, decreasing with increased warming, then there'll be more warming. It'll be an amplification of warming. But if low clouds increase with surface warming, that would actually go the other way. It'll dampen the effect. That's low clouds. For high clouds, it goes the other way. High clouds decrease with warming, then you would get less warming. If high clouds increase the warming, you get more warming. So high clouds and low clouds go the opposite way. So how exactly the altitude effect is going to be in terms of changes in clouds starts determining the feedback due to clouds. So that's why it's difficult to say what will be the role of clouds. What, according to the best scientific assessment, which is the IPCC assessment in 2021, what it says is that we think we have understood the low cloud behavior. Namely, that the low clouds are going to actually not change much with warming. They're going to remain pretty much what it is. High clouds is a little bit more iffy because we don't have enough knowledge about it to say which way will it go. And it relates not just something fancy about clouds, it's because the whole cycle of convection and cloud formation and precipitation. How does convection affect high clouds is still very much an open question. So that's why it's difficult to say something about high clouds. So because it's difficult to say something about high clouds, the total cloud effect is a bit of uncertainty. So it's not clear that what will be the cloud effect. Although, as I said, the latest indication is the low clouds will probably not have much effect. High clouds, the most, the best guess is, this is the guess, best guess is that it will actually increase slightly. So it will amplify the warming. So the best guess answer would be that cloud effect is going to be slight. It's going to be amplifying the warming. The water vapor effect, that is the gaseous phase water effect, is probably going to be more dominant. Cloud effect will sort of cancel off. And for clouds, there's also a shortwave effect. So the cloud effect is supposed to be, as I said, the net cloud feedback is not going to be much, according to the best guess from models. But yeah, I would just stop there. The best guess effect is that very little additional effect by the clouds, which means that most of the feedback may be due to the water vapor that comes about.
Okay, just last. So is there any change which you are seeing when we see that aerosols are reducing and greenhouse gases are increasing as in the last 2 decades? Do we see any change in the clouds?
Do we see changes in what?
In the clouds.
No, actually, there's a paper, I didn't mention the paper, but we actually have a paper in press which says that the net cloud feedback over the last 2 decades when we had the satellite observations is exactly zero, with a big uncertainty bar. So there's a short-wave uncertainty bar in the positive, there's a long-wave uncertainty bar in the negative. You take the effect of the two, it's net cloud effect over the last 20 years.
But that is regional or global?
No, global. Not regional. Regional just has more errors. So, it's not possible to talk about regional in the context of a 20-year time series. It's a very small time series. But you can talk a little bit about the global effect, and the net effect over the 20 years is a net zero feedback from clouds.
Okay, thank you.
Thank you, sir, for this talk. Very fortunate to hear you here. So my first question is, based on this IPCC 2021, the feedback word is now coined very effectively. I want to know that how the feedback introduction to these climatic models will affect our understanding, the numbers we are talking about. So introduction, yeah, more on that, the feedback.
I'm sorry, what? I'm sorry, can you repeat the question?
So yeah, so basically the feedback that we are more talking about based on this IPCC 2021, there has been more discussion on the feedback term. So I want to know how the introduction of feedback in the climate models makes it more complex, or maybe change our understanding of the climatic system, or maybe change the numbers that we are already talking about.
You are asking about feedback of climate change to aerosols and
No,
greenhouse
the
gases?
feedback we talk about adding the feedbacks to the climatic models.
So if I understand your question, we are not like mechanically adding any feedbacks. This is just part of the solutions coming from the equations you're putting in the model for clouds, for the water processes, etc. So I don't understand. I mean, we're not mechanically putting any feedbacks in.
Okay, I'm maybe not able to.
No, please repeat your question. I want to understand it better.
Okay, maybe after that,
Yes,
I can discuss.
you may interact afterwards. We can take some more questions.
But you had another question, I think, right?
Yes, there are some. Yes, Kamran.
Thank you, sir, for your informative talk. So I have a question that you shown that due to the decrease in aerosol concentration, the warming has increased. So if I have a question that if aerosol would not decrease and if was keep on increasing as the greenhouse gas was increasing, then the radiative forcing was not that much increased. So if aerosol was increased, so you still see that the extreme event that we are looking now. So if it will happen that if aerosol was increased.
So are you talking about the forcing by the aerosol?
Yeah.
So is this the diagram you're talking about? This one?
Yeah, means my question is if aerosol was not increased, then if the aerosol was increasing in the same fashion, then the relative forcing would be zero around.
You mean
Because
the aerosol force is increasing
yeah, yeah,
along with the greenhouse gas?
yeah, along with the greenhouse. Then the relative forcing was not much increased. Then if you think that if it was happened at that time, so we will not see any extreme events like that. If the greenhouse gas also increases.
Yeah, if the two forcings are offsetting each other,
Yeah.
then you would not see any change.
But the lifetime of aerosol and the greenhouse gas are different. So maybe their feedback also.
No, but you're asking a hypothetical question.
Yeah,
if
yeah.
They're increasing.
Yeah.
But I don't think that's what's happening in the real world. Greenhouse gases are increasing at a more faster rate than aerosols were increasing. That's why there's a net warming, despite the aerosols being there.
I'm just asking because if we have to make any strategies for the future world, so if it just some happen that if you want to should increase the aerosol to just a zero relative forcing.
You mean like a geoengineering project?
Yeah, kind of.
Yeah, that's just a different topic. The issue is more complex than just talking about global mean changes. This diagram, for example, refers to global mean. And sure, you can add a degree of aerosols which completely compensates the warming, the forcing by greenhouse gases. But remember this, the time scale for greenhouse gases is many decades, centuries. It's a CO2, it's at least a century. Aerosols, you gotta keep constantly replenishing the atmosphere with aerosols to be able to compensate relative forcing all the time. But besides that, the time constant or the life cycle of aerosols is a very short one. So the two things are not really very compatible. And then if you're talking about geoengineering, you're talking about other implications of geoengineering, not just compensation of forcing and temperature, but precipitation. It's quite a difficult subject to deal with. And I'm sorry, I don't have time to discuss the geoengineering in detail here.
Thank you, sir.
You're welcome.
Professor Pallamarajan.
Thank you for the nice talk. My question is just basically more curious on this particular topic, this particular slide itself. When you have this aerosols are decreasing, then this uncertainty is there here in this particular IPCC 2021. So the total anthropogenic forcing, next one should have a much smaller error bar, is what my guess is.
Yeah, I mean, if you just get rid of this side, sorry, you guys see my hand. Sorry. If you get rid of this portion,
yes, that particular,
you're left with just this.
That's right.
It will have much less uncertainty. In fact, then the uncertainties would be just this one here, CO2.
Okay.
10%.
I hope all the scientists of aerosol doing research in aerosol would not be out of job.
No, it's but one thing. This is sort of an interesting thing point which I didn't deal with. All this is human influenced aerosols. When we are looking at feedbacks, there are couple of interesting things emerging from models which are doing even more complicated systems where they include biogeochemistry. Two things happen. One, dust suddenly becomes not a static aerosol in the sense not doing nothing, but it actually becomes a bit active because as warming goes on, you create more arid surfaces because there are regions which are going to go semi-arid and semi-arid will go to arid. So you're going to form more non-vegetated land surfaces. Those areas create more erosion and therefore more dust emission. And more dust into the atmosphere is like a feedback. It's going to reflect more sunlight. So suddenly now you have natural aerosol reflecting sunlight, not because it was introduced directly, but it was introduced indirectly into the atmosphere. That's number one. Number two, it turns out that increasingly models are showing, especially models with interactive chemistry, that in the southern hemisphere, warming causes an increase in surface wind speed over the oceans. Increased surface wind speed means more sea salt bursting, more sea spray bursting, which means more sea salt in the atmosphere. Again, a feedback. Natural aerosol introduced into the atmosphere indirectly causes a reflection. So we got to be a bit careful whether this number in aerosols will ever come down to zero. It may be that we get rid of the anthropogenic part. There could be a natural part with increased warming, because as you remove the aerosol, the anthropogenic aerosol, you're going to get more warming. More warming could exacerbate natural aerosol. So I'm not sure if the aerosols will completely come down to zero.
But that, but that would be, reasonably well, could be modeled, the effects that you are talking about in
Yes.
terms of.
Yes, they are being modeled.
Then the human introduced anthropogenic sources, which.
Except that, though any aerosol has a very short lifetime. So trying to model surface wind speed, boundary layer, and then the aerosol, all that is still going to be riddled with uncertainties. Definitely more uncertainties than CO2 would have.
Yes.
That's.
Yeah. Thank you very much.
I mean, I'm just curious to understand that this uncertainty in the aerosol part in terms of determining the effective radiative forcing, is it because of the lesser understanding of the nature of aerosol, or is the processes that are less understood?
Both, because the inhomogeneity also creates this uncertainty in the process of how it's removed from the atmosphere. Dry removal, wet removal, up in cloud, below cloud, due to rain, and all that is part of the uncertainty. So it is process uncertainty is also there in addition to emission uncertainty and the life cycle uncertainty. So when I say life cycle uncertainty, that process is included in that.
Hello, sir. Can you talk something about a carbon neutrality plan? What are the steps?
I'm sorry, what?
Carbon neutrality plan, like reducing CO2 in the atmosphere. And is it possible with this population?
You mean how to reduce carbon in the atmosphere without human beings acting on it?
No, carbon neutrality plan is there, right? To reduce the CO2 by 2060.
Yeah, yes. What do I want to say about it? It's there, it's a plan. Is anyone following it? I think, so jokes aside, there's actually a serious effort in considering both the carbon dioxide removal, both in the marine setting as well as in the terrestrial setting. There are some very, very nice ideas there. The carbon removal in the ocean to deep sea sediments is actually going on. I think the problem there is that it's not proven to be, something that pays back. You're consuming more energy in putting it there in deep sea sediments, than what you are taking out. So it's not a net benefit as such, as of now. People are trying to also do it over land, put it in surface. I don't think that is advanced as far as the marine carbon dioxide removal. But there are serious efforts. There are some serious thoughts going on how to make it efficient. Once it's efficient, then it would be a very viable process to attain carbon neutrality. And the other thing is, on the emission side, now a lot of sectors are having plans to, in their own individual sense, to go to net zero carbon emissions in the next 3 decades. So they are actually ambitious plans, but they are practical too. There's some real effort that's being put in to go to net zero by 3 decades.
So I'm again here.
Yeah.
People who study paleoclimates, we always believed hydrological cycle is the driver of climate. Now we know for last several decades, we have been told CO2 is the driver. So what is your opinion?
In paleoclimate?
Yes. No, I mean, whether CO2 is the driver of climate or it is the hydrological cycle.
I think if you're talking about paleo, it's really difficult to say. It's interactive. CO2 has had an effect, but really how the whole carbon cycle behaves is still to be, I think, comprehensively understood. Like, for example, if you talk about going from ice ages to the glacial periods and back to ice ages, certainly it seems like the carbon removal or carbon appearing in the atmosphere seems to be something triggered by circulation, deep ocean circulation. But then once the carbon gets into the atmosphere, then it sort of becomes global amplification effect by CO2. So it depends on, I guess, where you want to cut things and start from, because it's a cycle. It's how it's happening, on what time scale it's happening. That's a question. That's a question that's still going to be solved. But basically, in the biogeochemical cycles, you have the carbon freed up. It appears maybe in the southern part of the system, climate system, goes in the atmosphere, and then warms the whole world. And then something happens, which then makes the cycle go the other way, and carbon gets locked up in the deep ocean. So exactly where do we want to start with the cycle? It's a whole CO2 biogeochemical cycle. To me, I don't know where to cut it.
Can I? Okay. Very informative talk. Thank you for that. I have one or two questions. You showed humidity increasing global. That is, I think, at the surface. But what about water vapor in the upper troposphere? Or is there any evidence?
So relative humidity is increasing in the upper troposphere.
Oh.
So doesn't mean that water vapor is increasing. It just means relative humidity is increasing in the upper troposphere. There is evidence for that from satellite data. It's kind of something which is not as prominent as the lower atmosphere, but it certainly seems to be increasing in the upper troposphere.
And number two is total precipitation. Because your talk is mostly on precipitation. India doesn't show a significant change for last 100 years. So, but you are saying so many changes.
Actually, it's not so. Let's see if I can. These are slides I didn't show. Let me see if. Okay, no, not this one. Okay, so this is actually work that we did some years ago. If you look at, okay, so this is actually only North Central India. But
Regional, yes.
Right.
But all India, I think.
All India, the model doesn't show necessarily that all India is decreasing.
Yeah, that doesn't.
Yeah, because. Sorry, I had to just answer Shamla's question. Just 1 second. So all India is, it's not consistent all over India. So, presentation.
There was somewhere this weakening of monsoon.
So you see this one, this is the, if you look at this model. So if you look at the all June, July, August precipitation, there's the last 50 years of the 20th century. You don't see a decrease all over India. You see a decrease in the North Central region, then you see sort of a slight increase here. So it doesn't change the same way all over India. And as I said, in the precipitation, when you start looking at small regions, it also has larger statistical significance problems. So I think in North Central India is now something that really every model is getting now. So I think that's fairly reliable. The whole of India, it's very difficult to talk about the trends.
Okay, so due to time constraint, this will be really the last question. Swagatika, please ask.
Thank you so much, sir, for such a nice talk. My question is mainly in climatic research, the time period after 1970s, it has been prioritized for aerosol and greenhouse gas effect and its effect on precipitation. During this period, there is a enhanced warming as well as a hiatus, temperature hiatus. Similar pattern is also observed in the past. That is the early 20th century warming because of greenhouse gas and the subsequent global cooling. So there are very few research during this for this period. What is the effect of this temperature variation on precipitation? So more research, digging more deeper into this period and the effect of temperature on precipitation, The understanding, it will enhance our current knowledge. So what's your view on this?
Sorry, I didn't get the full thrust of the question. Are you saying that around 1970s, greenhouse gas? And-
After 1970s, there is enhanced warming and also a temperature hiatus followed by this enhanced warming. So similar pattern is also observed in the past. That is the early 20th century warming followed by the cooling, global cooling. So in literature, there are many studies regarding the effect of this temperature pattern or this greenhouse gas as well as aerosol on precipitation. For that period, there is there are very few studies for precipitation. So I think digging more detail into this period will enhance our understanding. So what's your view?
So okay, so I'm looking at this plot here from 1970, you're saying there's an increase in temperature, right? There's an increase, sharp increase in temperature from 1970.
Yes.
And you're saying that what effect it has on?
Before 1970?
Yeah.
Early 20s, there is a warming as well as a cooling.
This
After
one?
this,
This one?
yes.
This cooling?
Just from 1901 to 1940, 45.
Okay.
Then there is a cooling.
Yes. So if you look at the magnitude of this, and if you look at kind of what the the changes are, it's very small. And this could be due to just internal variability because we know the forcings by either greenhouse gases or by any other constituent was very small over this period. So there may be a component due to internal variability that's responsible for the cooling over this period. Because we don't know of any known forcing at that time, in this time period, that would give rise to an apparent cooling.
Cooling after 1945.
Okay, Swagatika, I think that we can discuss this later because of some time constant.
After 1945? That would be here, right? This cooling?
Yes.
Again, this portion you're referring to, is it?
Yes, sir. This cooling and the warming before that.
This cooling and then this one. This cooling again, that there's no sort of explanation from forcing itself that you can reproduce it. But if you look at the model variability, you see the model variability, if you look at this envelope of the orange curve, I mean, it is of the same order. And the shading essentially is one manifestation of internal variability in models. So I would sort of say that compared to this portion here, where this curve is clearly rising above internal variability, this curve is not. This portion of the curve is not. So it's quite plausible it's due to internal variability there. But you can't make the same argument on internal variability in this portion because it's so standing out above the noise.
Yes, sir. Thanks.
Did that answer your question? Or not?
Partially.
Okay.
So yeah, some more questions can be asked after this colloquium. So thank you, Professor Ramaswamy, for taking so many questions from a very diverse audience and on different types of questions. So may I request now our director, Professor Bharadwaj, to honor the speaker with a memento.
Oh.
So with this, I would like to invite my colleague, Dr. Vineet Goswami, for vote of thanks.
So friends, we have reached the conclusion of today's episode of PRL ka Amrit Vyakhyaan. And so I would like to thank our colloquium, our Vyakhyaan Karta, Professor Veer Ramaswamy, for accepting our invitation and coming to PRL to give this talk. And it was really a nice talk and to look into what the future holds for the mankind. And I would also like to thank you for taking all the question and answers from our audiences. Yeah. And next, I would like to thank our director, Professor Anil Bhardwaj, for his constant support and motivation for carrying on with these events, PRL Kamrit Vyakhyaan. And then I would like to thank, next, I would like to thank Dean, Professor Pallam Raju, and his office staff for all their support and support for conducting these events. And I would also like to thank all the members of the PRL Kamrit Vyakhyaan committee to make this event possible. And again, I would like to thank all the audiences for coming here and as showing their enthusiasm to make this event a success. And thanks to Dr. Narendra Ojha for handling the question and answer session. And do visit PRL website and other social media platforms to know more about upcoming events at PRL, especially PRL Kamrit Vyakhyaan. And with these words, I would like to propose for the closure of today's event. And I would now like to invite you all for a cup of coffee or tea outside. Thank you very much.